Now we're going to turn our attention to reactions of aldehydes and ketones. We will first look at a few reactions we've already seen, including reduction and some examples of nucleophilic addition. So we know that we can carry out electrophilic aromatic substitution as a way to make a ketone. So if we have benzene and we treat it with acetyl chloride in the presence of aluminum trichloride, we will make acetophenone. Now from here, what can we do with the carbonyl? Well, more recently we saw that if we have a ketone and we reduce it with lithium aluminum hydride or with sodium borohydride, then we will reduce the carbonyl to an alcohol. And the same thing over here. So these reagents are not going to touch the benzene ring, but they will add hydrogen in the form of a hydride to the carbonyl carbon, and then the oxygen is going to grab off a proton from the solvent. So the carbonyl is converted to an alcohol. But earlier, when we were talking about electrophilic aromatic substitution reactions, we saw that there was a potential problem of carbocation rearrangement doing Friedel-Crafts alkylations, but we saw that those rearrangements don't happen when we do an acylation, and so we saw that it was possible to do an acylation followed by a reduction to give the same product that would result from an alkylation without rearrangement. So we saw that there was the Clemmensen reduction or the Wolff-Kishner, and that both of these would reduce the carbonyl all the way down to a CH2 group. So using the Clemmensen reduction, that will give us ethylbenzene, and Wolff-Kishner would also give us ethylbenzene. Now, although we talked about these reactions specifically with aryl ketones, it's not necessarily an aryl ketone, but it does only work with aldehydes and ketones, and these will not work on an ester or an acid. So we have two different categories of reducing agents, two of them that will reduce the carbonyl all the way down to a CH2 group, and two of them that will reduce the carbonyl to an alcohol. We also saw some important examples of nucleophilic addition, where a nucleophile will share its electrons with the carbonyl carbon of either an aldehyde or a ketone, pushing those electrons up onto the oxygen. So that will give us the benzene connected to the carbonyl carbon, which is still connected to the hydrogen, still connected to the methyl group, still connected to the oxygen, but now by only a single bond because one of these pairs of electrons moved up onto the oxygen. So we have the two lone pairs that were already present and another lone pair from what used to be the double bond, and so this oxygen has a negative charge. This is an intermediate, and then after aqueous acid workup, the O- can grab a proton, and that will give us this alcohol product, where this piece came from the Grignard and this piece came from the carbonyl containing compound after protonation. In addition to Grignards, this can also be done with organolithium reagents. Once again, that is a source of a nucleophilic carbon that will push these electrons up here, giving us as an intermediate this. And then after aqueous acid workup, the O- will grab a proton, and we will end up with this alcohol. And a third example, if we start out with a terminal alkyne and we treat it with a strong base such as amide. The amide is going to pull off this proton, putting these electrons onto the alkyne carbon, and that will give us this anion. Technically, it would be the sodium salt. And then treatment with aldehyde, so in this case benzaldehyde. This nucleophile will share its electrons, push these electrons up onto the oxygen, giving this intermediate, and then aqueous acid workup. The O- will grab off a proton, giving us this alcohol as our final product. So we've already seen examples of nucleophilic addition where we have very strong nucleophiles that can share electrons with the carbonyl carbon of both aldehydes and ketones. In addition to hydrides such as sodium borohydride or lithium aluminum hydride, and organometallic species such as Grignards and organolithiums and alkyne anions, there are many other types of nucleophiles that can carry out nucleophilic addition with aldehydes and ketones. For example, if we have acetaldehyde, we can react this with water. Water can act as a nucleophile, resulting in the formation of a hydrate. An aldehyde can react essentially with hydrocyanic acid, where the cyanide is the nucleophile that adds to the carbonyl carbon, leading to the formation of a cyanohydrin. Alcohols can act as a nucleophile and react with aldehydes and ketones. This intermediate is analogous to the other types of species. This will actually react with a second equivalent, leading to what's called an acetal. A primary amine can react with aldehydes and ketones to form an analogous species, and then this will undergo the loss of water to form an imine. And a secondary amine will also act as a nucleophile with aldehydes or ketones, giving this intermediate, which also loses water, to form an enamine. Now for comparison, if we were to react this with sodium borohydride or lithium aluminum hydride, we would get this, where let's say this came from the hydride reagent. And if we reacted it with a Grignard, we would get this, where the R is what came from the Grignard or the organolithium. Just as we've seen with hydrides and Grignards, for example, acting as nucleophiles and sharing electrons with the carbonyl carbon, resulting in alcohols, other nucleophiles can also add. In each case, we get an analogous tetrahedral complex. And so these are analogous to these, but in some cases, additional reactions happen so that we get something that looks a little bit different. But still, in all of these cases, we're talking about nucleophilic addition. One difference, if you'll notice, these are all equilibrium arrows, and so these are reversible nucleophilic addition. Whereas adding a hydride or a Grignard or organolithium, these are irreversible nucleophilic addition. Try to think about, once this is formed, can this go backwards? That would require kicking out an H-, and that is not going to happen. If we tried to get this reaction to go backwards, then it would have to kick out either an H-, or to truly go backwards, it would have to kick out an R-. And so these reactions are not going to happen. So while these nucleophiles will add irreversibly, Other nucleophiles will add reversibly. So here we have an overview of many other types of nucleophilic addition. We are going to go through all of these in detail in separate videos.